So in this video I'm going to talk about radioactive decay. In the last video I referenced this graph which shows protons against neutrons, and we looked at a ratio of protons to neutrons. That ratio is really important because as the nuclei gets bigger, or as you add more protons, you've got to remember that the protons have a positive charge, and therefore if you add more of them, you need more neutrons to kind of bind the nuclei together, and the meson quark interaction helps do that. So as you add more protons, you need more neutrons to keep the nuclei stable. And when you have an unstable nuclei, you've got a radioactive element. So this graph we referenced in the last video. It shows the ratio of 1 to 1, but it shows that all the elements on the periodic table, as you add more protons, you need more neutrons. And then you get to this little island, or this little blob up here, and that's called an island of stability. And this is the band of stability. So we could imagine that you've plotted all the different elements on the periodic table, you've taken the ratio of protons to neutrons, and this is what it would look like. It's a kind of a sketch, not the actual one. So all the elements in here are stable, including this little blob, the island of stability. And any elements that would have a ratio out above or below the band of stability would be radioactive and would be unstable. So that's one way to tell if a substance is going to be radioactive. More obvious ways and more common ways, we're going to use the periodic table. So all the elements that are have an atomic number of 84 and greater are all radioactive. All the elements on the periodic table that have a mass number in parentheses, they're radioactive as well. So that means that that's more of an estimation of the mass, and it's not an actual value because it's too unstable to measure. It's too radioactive. And then all radioactive isotopes. So all the elements on the periodic table have isotopes, different versions with different numbers of neutrons that are radioactive. So that's how we can tell whether something's going to be radioactive. So the next thing to talk about is, if a substance is radioactive, how does it become more stable? It can't exist in that unstable state. It needs to stabilize. So it undergoes radioactive decay. And so the goal of it is for the nuclei to become more stable. Varying amounts of energy are released when something undergoes radioactive decay. And we'll look at each different type of decay. And in the first two cases, well actually in all the cases, there's particles released. So you create a different nuclei, and also there's some energy, and then also a different particle is released as part of this stabilization process. So in the next video I'll actually talk about half-life, which kind of incorporates how long it takes for something to become more stable, so how quickly something undergoes radioactive decay. So there's three main types of radioactive decay: alpha, beta, and gamma. Alpha is represented with this Greek symbol, Greek lowercase a, kind of looks like a fish. It's also a helium nucleus. So an alpha particle is a helium nucleus, which looks like this. So inside the helium nucleus, obviously you don't have electrons, so it's just an ion, so it doesn't have any electrons. So it's got 2 protons, and then inside the nucleus you've also got 2 neutrons, so that's how we have a mass number of 4, an atomic number of 2. It's got a charge of +2 because it doesn't have any negative charge to cancel out the 2 protons. So you'll sometimes see or hear it described, or hear alpha particles described as helium nuclei, and that's another way to represent it. In nuclear chemistry, very often you don't include the charge, but I'll include it there, but we won't include it as we do examples and as we work on nuclear equations. So an example of a substance that undergoes alpha decay would be this element, 241, 95. So remember, that's how we represent it. We have the mass number up here and the atomic number down here, and obviously the symbol right there. So the goal with balancing or showing radioactive decay is very similar to the balancing work we did, except what we're really focusing on here is making the numbers of protons and neutrons the same on both sides of the arrow. So we'll have an arrow here. So what we're looking for is total of 241 up above and a total of 95 down below. So we want the mass numbers to equal 241 when we combine them together, and then the atomic number to be the same as well. So an example of that, or the example of alpha decay. So we get an alpha particle produced. So then we could figure out what the other particle is, because we know that we've got to take a number, add 4 to it to get 241. So obviously that's 237. And then 95 is equal to 2 plus 93. So what we did was take this number, this mass, and make this mass equal to it. We know that it undergoes alpha decay. Well, that's in an exam situation or in a problem situation, and I tell you that you get 4 plus 237, so that equals 241. 95, you know that you get this 2 produced, and then also this number's got to be 93. And there's only one element on the periodic table that has an atomic number of 93, and that is Neptunium, or NP. So this is how we represent radioactive decay. This is an example of alpha decay. Basically, your goal is to make the mass the same on each side of the arrow. So the idea of conservation of mass still applies. Conservation of matter, in some ways we create a new element, so slightly different way of looking at conservation in this example. We also get a lot of energy produced. That could be in different types. That could different types of energy. That could be heat, light, UV light, infrared radiation. So different types of energy. So basically, you've gone from an unstable situation, energy is given out, so more potential energy to a less energetic state. You can't create or destroy energy, so the energy that was holding this isotope together is released in a different form. But the amount is the same, the type is different. But basically, just to hammer this point home, and I know I'm repeating myself, basically we're taking an isotope, and we're making sure that if we start with a mass of 241, the mass on this side must be the same. We know that we get this alpha particle produced, and that helps us figure out what this number would be. Okay, alpha particles, just as just a note of reference, a piece of paper, or probably a thick piece of cardboard, could probably stop alpha particles. They aren't very penetrative, so they don't go through wood or anything like that. Where they become really dangerous, if you ingest them in some way, or you swallow some, or you breathe some in, then they become really, really dangerous. And we'll learn more about the effects of radiation in a different video. So another type of radioactive decay is beta, and the symbol is kind of a uppercase B with a longer stem. That's the Greek letter for beta. And so the particle that's produced, as well as a lot of energy, so there's a theme running all the way through, you get an electron produced. Could also be a positron, which I'll show you an example of each one. So you take a radioactive substance, and let's take cobalt 27, and it undergoes beta decay. So we represent that with an arrow. You might see it also written like this, with the type of decay written above the arrow. That kind of prompts you to write the particular particle that's associated with that radioactive decay. So a beta particle is an electron, and the way that we represent it is slightly different from what we've already learned, because down here we're going to write this -1 to represent the charge of the particle, and then up here we represent the mass. So in the same way that the mass is represented up here by this 60, that represents the number of protons and neutrons added together, mass number. Electrons don't have a significant mass, so we just put a 0. So then the other particle that's produced would be 28, which is... So we take a sample of radioactive cobalt, it undergoes beta decay, it spews out electrons, and also creates this new particle of nickel, which is more stable than this. So, where does this electron come from? And I'll answer that question now, because that's an important idea. The idea of a beta decay is that a neutron inside the nucleus, and we represent a neutron like this. So down here will be the charge, up here will be the mass. So electrons have zero charge, zero mass, -1 charge. Neutrons have zero charge and a mass of 1. So a neutron changes into an electron, which we represent in the same way, and then a proton, which has a mass of 1 and a charge of +1. Might be a little small to see, but mass of 1, charge of +1. So same sort of idea of balancing equations, making it the same on each side of the arrow. Same idea with up here, making the number of protons and neutrons and the overall charge the same on both sides of the arrow, or equal. Same sort of idea here. This needs to cancel out to 0. -1 + 1 gives you 0. And then 0 + 1 would give you 1. So everything's equal. So this neutron inside the nucleus of this isotope changes into an electron and a proton. The proton makes this number go up by 1. So it goes up to 28. So it starts off as 27. This happens. This particle gets released, goes off and combines with something else, and then you're left over with this version of nickel. The mass number stays as 60 because you've taken something with a mass of 1 and then you've created something with a mass of 1, so there isn't any change in the mass number. So that's an example. That's the most common version of beta decay, and that involves electrons as the particle, and obviously a lot of energy as well. I forgot to mention earlier, these two types of decay, alpha decay and beta decay, if you take a ratio of neutrons to protons and you end up with a ratio that's out here, so it's above the band of stability, that's when you get these two things happening. So you get alpha decay or beta decay. Sometimes you can have both. You can have a series of different radioactive decays, and we'll look at more examples of that too as well. So when the ratio is too high, we'll get one of these two types of decay. So let's look at positron emission, because it's slightly different. So in the previous example, we had a neutron changing into an electron and a proton. This time we take a proton, which we represent P for proton, obviously, mass of 1 and a charge of +1. And that changes into a neutron, which is going to stay in the nucleus, and an electron. Excuse me, a positron. So this is called a positron. It's also called an antimatter electron. It's basically an electron that has the same mass but a different charge. So again, we can double check our balancing here. Mass of 1, 1 plus 0 is 1, obviously, +1, +1. So this happens inside the nucleus. To show an example of that type of decay with an element, we can just use cobalt 60 again, just to show the example. If it undergoes a positive version of beta decay, which we represent with this little plus sign next to the beta symbol, that would be 0 + 1 plus 60. And element 26 is the glasses iron. Okay. So same idea. You need the numbers of protons and neutrons to be the same. So 60 on this side, 60 on this side. 27 is equal to 26 + 1. So all is well. So two different versions of beta decay. If you were ever given any kind of problem to solve involving that, then you'd be told it was beta, one version or the other, so you wouldn't have to memorize that. This type of decay, this positron decay, happens when you've got excuse me, a ratio of protons to neutrons that's below the band of stability. All right, so let's look at gamma, which is the most dangerous. It can penetrate through wood, through clothing, through skin. It can go straight through a human body, which is kind of dangerous. So it's the most penetrative. So the idea of gamma, we can start off with an isotope of cesium. So there's no real there's particles produced, but they're light particles. So it's not necessarily a particle like an electron or a nucleus or a small nucleus, that kind of thing. It's light particles. Excuse me. So if something undergoes this kind of decay, it's usually associated with another type of decay. So cesium, this isotope of cesium undergoes a beta decay, and it produces an electron. So that's why this number is 56 and that's 55. So it undergoes beta decay, but then you've got this version of must be a barium. Oh, never memorized the periodic table. So barium has, or this isotope of barium is in a highly excited state. It can't stay like that for very long. In fact, it stays like that for a split second, and then it produces a different version, because we've already undergone one type of decay, but we need more decay to make the nuclei more stable. So what actually happens is that this version of barium goes to a less excited state. And photons are produced, or light particles are produced. So we go from unstable nuclei to through one type of decay, in this case beta decay, but it could also be alpha decay, creates this highly excited, highly energized isotope, and then that eventually undergoes another type of decay, in this case gamma, and produces lots of light, blinding light. So a huge amount of energy released. So, to recap, we're looking at radioactive decay. It's the process that unstable nuclei, or radioactive nuclei, undergo to become more stable. We can analyze that on a graph like this, having neutrons plotted against protons. Elements that are outside this island or band of stability, they're too high or too low, they're going to undergo one of these types of decay. This is how we can tell, using the periodic table, which elements are going to be radioactive. All elements have radioactive isotopes. Some of them are more stable, some of them are less stable. The three different types of decay are represented with these equations. Very similar to the balancing work we've already done, but this time we're balancing the number of protons and neutrons. And we're going to look at the mass number and the atomic number to help us do that. Your goal will be to memorize the different particles that are associated with the different types of decay. And that's radioactive decay.